Chapter 21 deals with malicious code and application attacks. We're going to be taking a look at some examples of these attacks, malware injections, so you can see things firsthand. I'll also give you a little bit of a sneak preview of what CEH is like, but sometimes it helps to hear things conceptually and actually see it in action, and it's kind of a nice break from nothing but PowerPoint. So let's take a look. All right, malicious code in general, malware, malicious software, potentially unwanted programs, viruses, worms, Trojans, adware, etc. The list goes on and on, the different flavors, different characteristics, behaviors that are exhibited by the malware. The term virus is used loosely to describe really any flavor of malware, which sometimes it's a little bit inaccurate or inappropriate. I believe you have a virus on your system where your attacker has remote control. Actually, that's a Trojan. Viruses infect executable files, deliver a payload, may transform or encrypt themselves, and replicate if you're looking at the characteristics. But we understand what you're saying when you use virus as a catch-all. We're going to look at some examples, though, of different types of malware and the characteristics or traits exhibited, just to get a feel for a couple different categories. All right, so where does malicious code come from? Well, first, it comes from skilled malicious software developers. Okay, those are the nastier sources of malware. Script kiddies will download malware or download pen testing or hacking tools developed by quote unquote real hackers. Every bit is dangerous. However, script kiddies often don't have a lot of regard for the gravity of their actions or the consequences. It's kind of like a kid with a loaded gun. Our amateur code developers and then advanced persistent threat groups, these are also the scarier variety. So skilled malicious software developers, government agencies, things like that potentially, and advanced persistent threats, which we defined earlier in the course, is a group of extremely skilled, extremely motivated hackers working towards a common goal. Oftentimes they're somewhat of a cyber mercenary. All right, viruses. Viruses infect, they replicate, they deliver a payload, much like a biological virus. They can't survive outside of executable code, kind of like a biological virus can't survive outside of the cell that it invades. Viruses propagate by infecting, once again, executable code, which might be in the form of the master boot record, which is the first code run when the system boots. It does contain executable code. It contains references to what partition to mount, file objects to call, and so forth, but it is executed every time the system starts up. File infectors will infect executable files. There's various different flavors of that. A companion virus is really not a virus that infects a file. It's a malicious copy of a file with, say, a different extension that has a detrimental effect. So notepad.exe, for example, is a legitimate system file. You might have a notepad.com that is the malicious alter ego version of that. Sometimes call that a companion virus. It really doesn't satisfy that requirement of infecting executable files. Okay, macro viruses. Macros are functions within Word, Excel documents, spreadsheets, that sort of thing. They're written in Visual Basic for applications, and you can have dynamic code inside of a document, which are typically non-executable files, but they have additional functionality that can be launched from within the file. You have similar issues with PDFs. PDFs can contain malicious JavaScripts, same end result. A service injection virus allows you to inject into another running process. I'm going to show you an example of that here in a second, where I'm going to inject into Internet Explorer, for example, but it's really going to be my remote access Trojan that is trying to evade detection by hiding as Internet Explorer. Very cool. Wait a minute, you can do that? Oh yeah. Lots of different flavors of injection. All right, virus technologies, multipartite, or what I like to call equal opportunity infectors. They infect both the boot record and executable files. Stealth viruses try to direct scans of the file to a clean, uninfected version of the file. So they try to evade detection by diverting scans away from the infected file, changing references in the file system, that sort of thing. All right, polymorphic viruses create varied but operational copies of themselves. They use a mutation engine. We still rely heavily on signature-based detection. We've talked about that. Signatures require specific pattern matching. When I alter the code, the signature is no longer the same signature, polymorphism or metamorphism. And then what better way to evade signature-based detection than to encrypt the virus? Well, if it's encrypted, I can't identify it, I can't inspect it, I can't reverse engineer it, it's encrypted. However, when it decrypts itself for execution, at that point it's vulnerable and it can be potentially identified. All right, so the hoax. Yeah, the hoax is a, what's a hoax? You get an email saying, we got this nasty malware floating around, and if you install this software on your system will be patched and won't be vulnerable. And the patch they want you to install is actually the malware. So if you remember back in the earlier days, 1999 and later 2000s and so forth, we could still send a lot of executable attachments in email. Oh, you just cringe when you think of how much of that stuff was infected with Trojans. Okay, logic bombs characteristically lie dormant, wait for a triggering event before they launch their malicious payload, whatever that may be. A time bomb, excuse me, would be a logic bomb with a date time condition. So on January 1st, 2001, launch a denial of service attack against Microsoft. Or user runs an application, executable, keystroke sequence, whatever. All right, Trojan horses. The whole Trojan horse story deals with a giant wooden horse presented to the gates of the city of Troy with some Spartan soldiers hiding inside, unknown malicious payload. The horse is taken inside the city walls. The gates are closed. Everybody goes to bed that night. The door opens. Spartan soldiers jump out. Malicious payload executes. They open the front gates. The rest of the Spartans come in and kill everybody. So an unexpected payload residing inside of a seemingly harmless carrier, a giant wooden horse. Trojans don't typically replicate on their own. They're spread through repetitive downloads from a central source. And we talked a little bit about that in a previous chapter. We talked about bots and botnets, which we're going to talk about again. All right, rogue antivirus software could be a Trojan. Remote access Trojans give you remote access or remote administration. RAT, same acronym, different definition. In the hands of a network administrator, it's an administrative tool. In the hands of an attacker, it's an access tool. All right, crypto malware. Trojans may actually hide crypto malware, cryptocurrency mining. I install and infect your system with a Trojan whose whole purpose in life is to use your system's resources to perform Bitcoin mining, which can be highly lucrative. So these may actually participate in a botnet type of configuration. A bot is really a Trojan that participates with its buddies in the collective. The botnets, network of bots, network of Trojans, typically working towards a common goal. We diagrammed this out in a previous chapter. The botnet oftentimes coordinates attacks on a primary target. The bots are the agents. The zombies are the unaware that they've been infected victims. The agent handler model we talked about in the previous chapter, coordinated attacks on a primary target. All right, so let's take a look at the Trojan. I'm going to shift gears here a little bit, and since we're working off of a little less screen space here, but I'm going to keep it all in my virtual environment. So I'm going to shift gears a little bit, and let's go ahead and take a look at some examples. All right, so on my Server 2019 machine, for example, I've already created a Trojan, and I have infected my victim system. I've used a utility called Beast. I've wrapped the Beast server into a seemingly harmless tic-tac-toe game, Graffiti, and I've called it trustme.exe, and I've deployed it to my victim. All right, so I've already gone through the infection process. I'll have you come on back for CH for the rest of that story. But the end result is connected. Womp, 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 womp. You gotta do the sound effect too. All right, I've got a full file manager. Okay, find drives, upload, download, run file, run hidden, etc., etc. I got a full registry editor. Registry editor, ugh, that's the most powerful administration tool you have. Everything gets modified in the registry. Why not just go directly to the source? That you couldn't get more powerful than that. You just have to know what you're doing. All right, I got a full screen viewer and the ability to interact with the desktop. That's remote desktop. I could view the webcam if there was one. I could do running apps, running processes, services, set clipboard contents. You get the idea. But it shows up on the victim system in Task Manager as Internet Explorer. And it is right there. I don't really see that running in the system tray because it's not running. It's injected into. So there's an injected process. At first glance, it looks legitimate. All right, so that's an example of a remote access Trojan. That's one of the golden era of remote access Trojans. The Beast, Sub 7, Mo Sucker, Thief, etc. NetBus. Oh my gosh, I almost forgot NetBus. All right, so that's what a Trojan looks like, and it does give you nice access to a compromised system. It'll typically use covert channels, which is the unallowable use of an overt or authorized channel. We talked about that earlier. Tunneling inside of HTTPS, for example, is one of your better options for that. The worm is an autonomous program that propagates on its own. It doesn't have to infect executable files. It spreads oftentimes through sending copies out of itself to the recipients in your address book, at least years ago when we could do that. It also automatically detects weaknesses or vulnerabilities, RPC endpoint vulnerabilities, that sort of thing, propagates. A lot of times it carries a viral or malicious payload along with it. Code Red, RTM, the Internet Worm, and Stuxnet are all great examples of worms. Stuxnet was the first quote unquote cyber weapon, really elegant stuff. 7 days built in, and its whole purpose in life was to infiltrate uranium enrichment facilities to slow down nuclear arms development in countries we would be concerned about nuclear arms development. All right, spyware and adware. Spyware spies on or monitors your actions. The most rudimentary spyware is cookies. By visiting a website, it records cookies, which are notes about your experience. That's the sort of thing that makes it possible for you to get pop-up ads for a product on the next site you visit that you just looked at on Amazon. Cookies are also used to very sophisticatedly track your activities on the network. Sophisticatedly, I think that works. Very sophisticated way to track your activities on the network, on the internet. Lots of information collected about your web browsing habits. Spyware in general monitors your actions, transmits details to remote system, may include keystroke logging, which is potentially a lot of data. Adware displays advertising, pop-up ads, which may be annoying, but not necessarily too dangerous. They may monitor shopping, redirect to competitor sites, that sort of thing. Kind of annoying, but not too terribly malicious. And then potentially unwanted programs or PUPs are not necessarily malicious, but probably completely unwanted. If you've ever downloaded a file from an alternative file mirror, like download.net or downloads.com or other file mirror, sometimes you click through the download options a little too quickly and you miss the please install this, this, and this along with it. You install your utility and then all of a sudden your home pages change, you got weird browser extensions, and you're on askjeeves.com. It's like, how did this happen? Because you selected some installation options you didn't pay much attention to or didn't look very closely. So a potentially unwanted program might collect information, etc., which generally don't want that, but it isn't necessarily malicious, it's just annoying. So PUFs, and some of them can be kind of borderline. All right, ransomware. Ransomware, what a great business making model, right? Great strategy. You got to hand it to it. Great way to make money. I'm going to hold your stuff for ransom and you better pay the ransom or you don't get it back. It weaponizes cryptography, encrypts files to hold them hostage, demands a ransom payment. Paying the ransom may be illegal and generally not encouraged, since that just generates more of the same, right? You pay the ransom, they're going to be back, guaranteed. It's kind of like negotiating with terrorists. Don't give your ground. It's a different category altogether, but kind of. And the Colonial Pipeline hack not too long ago, great example of ransomware attack. I've got a student who came for several courses, to become a pen tester, and he makes a nice living niche marketing city municipalities, pitching the ransomware statistics and then selling them security assessments, penetration tests. All right, so EXEs are one thing, and then you got malicious scripts. All right, malicious scripts, libraries of scripts for automation to improve the efficiency and effectiveness of tasks. Scripts are great. They allow you to program your system to do things automatically. Fantastic for administration, but they can be written with a malicious intent. So APTs might automate routine portions of the malicious activity with scripts. They may use it to facilitate fireless malware. All right, the scripting interface on a Windows box has already been cleared as a legitimate system utility. So PowerShell, for example, that's a really important, powerful utility. Fileless malware may actually load PowerShell scripts into PowerShell and then try to hide in unobvious locations within the system, registry key objects and so forth. Fileless in general doesn't leave a footprint on the system because it doesn't actually install a file. And that's one of the easiest ways to get detected, is to leave a file footprint on the system. So they may inject into memory, and there's a lot of other mechanisms around that. But the whole idea there is we evade detection because we're not really installing any hacking tools. We're using authorized system utilities. We call that living off the land as well. And we're just running payloads from other locations. All right, zero-day attacks. We have defined this before. Security flaws discovered that have not been thoroughly addressed by the security community or addressed at all. There's a window of vulnerability in zero-day attacks. Actually, a little disconcerting. There was a couple surveys years back that they were looking at the average zero-day lifespan, and PricewaterhouseCoopers said it was like 312 days. Kind of like a year before somebody figures out this vulnerability is there, catches somebody exploiting it, and a patch is developed. That's a whole lot of compromise in 312 days. Slowness in applying updates is on the part of system administrators. So even if the patch comes out, we still have to test it. It's on a stack of other patches to test. We'll get to it when we get to it. So the defense in depth approach, overlapping security controls, we want additional mechanisms outside of just malware detection to stop zero-day attacks. We talked about this earlier: perimeter security, network access control, a couple examples of additional layers. And again, we reference a lot of this stuff in chapter 17. All right, malware prevention. We've also talked about this a little bit in previous chapters. We rely heavily on signature-based antivirus detection, which means you've got to program the AV exactly what it's looking for. That's great to reduce false positives, but it's not so great when you consider we have to know it exists to protect against it. So we do have heuristics, we do have anomaly detection, we've got code execution and a sandbox environment. We talked about a couple other options with that, but Windows is the most vulnerable platform to malware because it's the most widely used. It's been around the longest, and attackers will spend more time working on systems that give them a better return on their investment. Windows is so widely used that we find vulnerabilities in Windows, we're going to have plenty of Windows users to compromise. But all OSs do have some malware. All right, anti-malware software is, again, heavily signature-based detection oriented. Heuristics are behavior. We're looking at what it tries to do. The responses to detected malware could be things like quarantine, which really just removes the ability to execute it in the file permissions, or deletion, get rid of it. Sometimes we mistakenly recognize software as being malware, and if we were to fully delete it, then that might not allow us to restore it. Quarantine's a little bit safer because what if it's a legitimate file, we have to restore it. All right, typically anti-malware is best implemented in a centralized monitoring sort of capacity. It reduces the need to check for logs on all systems, endpoint detection, SIEMs can coordinate all that centrally. So there's something to be said for centralization. All right, malware prevention also might involve integrity monitoring. That flat out means making hashes of critical system files, hashing them every so often, looking at the results. Did the hash change? If it did, that file's changed. Also, signature-based detection for digital signatures, and we've talked plenty about that. Advanced threat protection comes under different names and packaging. endpoint detection and response, managed detection and response, user and entity behavior analytics, and next generation endpoint protection tools. Next generation anything tries to wrap multiple aspects into the same software, do it all in under one roof. I'm always skeptical about that just based on performance requirements. But feedback I get from those implementing next generation firewalls, they're pretty darn good. But I'm old school. I want separation of duties. I want distribution of workload. I want fallback. I want no single points of failure. All right, the application attacks. A buffer overflow is a violation of the physical memory space of a running application. Now, we did talk about this when we looked at our exploit rule. We looked at the 90-90-90-90-90. That was a NOP sled, often indicating a buffer overflow. We also talked about it in a basic format. We looked at divided memory space, logically and physically enforced. But revisiting that, okay, the buffer overflow is there's a logical memory segmentation and logical address enforcement on any operating system. So again, I'm just trying to illustrate a divided memory space, not the ringed architecture. All right, but say I've got something running under the system account and something running under Eric's account. All right, Eric is allowed to access Eric's memory space, but Eric is not allowed to access the system's memory space. That is off limits. The virtual memory manager should prevent that. You're enforcing logical addresses. But I can write to my memory space, and if I've got a buffer configured where a function in the programming language doesn't check the target buffer size, I can send too much input to it. So I've got an input field. Okay, Eric is now flooding, yada, yada, yada. When I go to send that input to the buffer, it's only 4 characters, but there's more data coming. So it overflows physically into adjacent memory space, and it invades the logically enforced space of another running application. So I push into the system's memory space, for example, shellcode, which is the malicious payload, and I push stack addresses or pointer addresses into just the right location. So I drop my malicious code. That's a skull and crossbones, by the way. I just got to put the knobs on the bones. I drop my malicious code into the memory space, and then I change address pointers to point the execution of the system level process to my malicious code. Cha-ching, malware executes. Now, it's a little bit more involved than that, but that's the basics on a buffer overflow. So buffer overflows are based on poor coding practices, which again, in the defense of the developers, security has not historically been their job. But you can use more secure functions and see that check the target buffer size. All right, a buffer overflow leads to the execution of arbitrary code. And they're at the OS level, they're at the application level, and there's stack, keep, format string, but we don't need to go too far down those roads. We need to understand the basic concept. All right, time of check, time of use, race conditions, and state attacks. Okay, in general, when something can happen out of order, it's a race condition. Like you want to download a PDF product you paid for, but you got to check out first and submit payment. If you're allowed to go straight to the download, that's a race condition. You bypass the step where you actually have to pay the money. Time of check or time of use could indicate an authorization of access at one time, and then something changes out between the time you're granted access and the time you do access, and maybe that's been replaced by sensitive data. There's a couple different examples of that, but the time of the check and the time of use, there's a discrepancy and something changes between those two time intervals. Okay, backdoors. We mentioned backdoors before. Backdoors give us front-end authentication circumvention, right? It's a backdoor. We're not going through the front door. We're going through the back door. That remote access Trojan I just showed you for the beast, that's a backdoor. Remote access Trojans often give backdoor functionality. Backdoors are also installed by the manufacturer for a way to get in when you can't get in otherwise. Maintenance hooks, things like that also qualify. Privilege escalation and rootkits. Okay, the rootkit is especially nasty. It's supposed to be a kit to provide root access, but it has superpowers in the matrix, so to speak, It runs as a device driver, which means it runs as part of the operating system. And in Windows systems, it has abilities you should never have as malware, hiding processes from the process table, for example. All right, let's go ahead and hide our beast. I'm sorry, that's a different box here. All right, so there's my calc.exe running. If I run the foo rootkit with the process identifier of 2212, you watch calculator just blink out of the process table. Bye, it's gone. It's still running, obviously, because there it is, but it's been hidden from the process table. Now, if I used a terminal window remote access Trojan where you could detach from console and execute the actual application window, I'd have no idea it's there. All right, so again, we dig into that stuff a little bit more in CEH, but that's what a backdoor looks like, and that's what a rootkit looks like. All right, injection vulnerabilities. I'm going to show you an example of a SQL injection. They'll give you a pretty good feel for how injection works. Your injecting in general is inserting something unexpected into. Now, we've just seen process injection. iExport.exe, that's the beast Trojan running. I don't see Internet Explorer running. That's a flavor of injection. I've also got SQL injection. Where I'm going to inject into a SQL query. So we're going to walk through this code here in just a second. And this is reliant on the lack of sanitization of user supplied input, which if you ever see that as a answer choice, sanitize input, validate input, whatever, you're going to consider that as a prime candidate for how you countermeasure various types of attacks, because lots of attacks are countermeasured by sanitization of user supplied input. All right, so injection, wide range of attacks. I'm dropping something unexpected or a payload into a pre-existing query, memory space, command window, LDAP database, XML file, local file, remote file includes lots of different flavors of injection. SQL injection, structured query language. We talked about SQL in the last chapter. We talked about database and database terminology. Structured query language allows you to interface with a database, selects, inserts, updates, unions, deletes, and drops. These are some of your basic SQL commands, but they also have stored procedures and extended procedures that allow you to do things above and beyond normal database interaction. So we're going to take a look at blind content and timing a bit. We're going to hit the slide here. We're going to actually depart from the slide. We're going to hit the demo. All right, Server 2019 box. I'm going to access my Coastal Bank SQL demo injection page. All right, this is a login for username and password. If I put in Eric and password, I'm going to get access as denied. Okay, bad logon.asp, got it. If I put in Bob and password, I'm going to get logged in, ebanking.asp. All right, if I look at the code, I'm running a query with the input provided in the form username and the password provided in the form password, and I'm dropping that into a SQL query. The SQL query is just matching a username and password pair in the database table. User info. All right, so I got Bob and password, and I've got Allison password. I don't have an Eric and password. Eric doesn't exist. Bad credentials. Bob did, Bob got logged in. Well, fantastic. So when I run the query, select star from user info, where username equals the submitted username and password, if they match, I get ebanking.asp. I'm basically asking a question here. True or false, this matches. If it's true, I get logged into ebanking.asp. If it's false, I get bad logon.asp. Sorry, thanks for playing. I've also got elevated privileges. SQL admin for the database connection, bad idea. But in the mind of the developer, I'm just ensuring it always has privilege to do whatever it needs to do. And after all, the user needs to know a valid username and password don't they? They do, but what happens when they hijack this entire query? Oh, yeah, I can inject into that query and I can completely change it to whatever I like running under the system account. That is bad, bad, bad mojo. All right, when I type in American password, I get denied. So the first thing you do as an attacker is you try to break something. So I'm going to throw in a unexpected character like a single tick, excuse me, and I get an unclosed quotation mark before character string and password equals yada, yada, yada. That means I broke something. That means it's not being sanitized. That means injection is possible. Okay, single quote or 1 equals 1, tac, tac, throws in a condition that's always true. Do you see where this is going? I'm asking a true false question and I'm supplying a true statement. I'm hard coding it to be successful. Submit. Yeah. So if I throw in a single quote or 1 equals 1, that's what the query looks like. Tac, tac is a comment character, which means see ya. The rest of the query goes away. So now the query that's been injected into takes on a completely different meaning. Select star from user info where username equals whatever, or 1 equals 1. If either of those are true, log me in. 1 is always 1, at least in this version of the multiverse. And I get logged in. Nice. That's a authentication bypass, tautology, or input validation attack. Now, there's way more to it than that, but that's what SQL injection looks like. So I can call different SQL commands. I can run stored procedures, extended procedures, but you got to come back for CH for the rest of that story. So that's what injection looks like. User supplied input is being added to a trusted query or statement, and I completely alter it. Now, I can do the same thing with LDAP databases, XML databases, or even DLL injection, which DLL injection or hijacking is typically calling a DLL from a different file path that's got the same name. And there's more to it than that. But DLL, anything that loads a malicious DLL, really quickly, the Windows DLL should be in the system directory. An application that calls a DLL doesn't necessarily check the full path. If you drop a malicious DLL in the same folder, it finds it first and it runs it. That's the down and dirty on DLL injection. All right, so now we've seen a little SQL injection. Oh, blind. I got to show you one more example here. I mentioned we'd show blind. Blind is based on timings. And you've actually typically use some cheat sheets for this. But I can ask a series of true or false questions, and the delay time in the response page indicates whether I guessed correctly or not. So, for example, if I was guessing the database name, I can guess the length of the name. If the length of the database name equals 1 character, then wait 5 seconds. I hit submit. That didn't wait 5 seconds. It's not 1 character. How about 2 characters? Nope. How about 3 characters? Nope. How about 4? Nope. 5? Nope. 6, 7, 8, 9, 10, 11. Ooh, 1001, 2, 3, 4, 5. Hey, 5-second delay. I guessed correctly. Yes, it does. This is where the burp suite saves a ton of time, or SQL map, because it does all that behind the scenes anyway. So absolutely. All right, so this is all manual mode to understand how it works, but that's what we have tools for in the burp suite or OWASP Zap or Web Scarab. Any of those web application analysis tools will automate that sort of thing for you. So that's a blind content, blind timing based SQL injection, and there's more to it than that. That's just getting warmed up. All right, code injection attacks. Again, LDAP, XML, command injection attacks where you're injecting system or shell commands into an interface. That could be basic terminal window commands. It could be calling a shell function within Java or whatever. It could be getting a web page or a PHP get page, uploading a web shell. List goes on and on. All right, exploiting authorization vulnerabilities. All right, exceeding the level of access that they're authorized. Like that. That's a horrible idea. SQL admin, that should be way reduced from that. This gives us system level access. I just can't resist. Let's do at least one more thing. All right, so if I've got system level access and command shell access, I can do net user ads, net local group ads, yada, yada, yada. I could deface the web page. Okay, so no cracks about my my programming. I wrote that myself. This is the original site. If I do a XP command shell extended procedure, which is a extended procedure that gives you command shell, yeah, I drop that in. I now have system level access with a command prompt. That's bad mojo. All right, I'm going to echo you are hacked into default.htm. Submit. Access is denied. It didn't work. No, I didn't log in. That's actually the expected response. When I go to victim websites and 10.0.0.200 and I refresh, I'm hacked. Sweet. What can you do from a command shell? Yeah, under system account. That's bad. That's really bad. So excessive privilege is a bad idea. All right, directory traversals, insecure object references. Okay, directory traversals, these typically exist more in Apache environments, but I got an example for you. All right, the IIS 5.0 platform was susceptible to directory traversal Unicode attacks. So you could actually encode. I can't talk and chew gum at the same time here. All right, you can encode your slash in Unicode, and IIS didn't catch it. So COAF in Unicode is a slash. And then you're calling a command prompt after traversing up the folder structure, calling a command prompt, and you're executing parameters in the command prompt. So this turns into this. That's not right. No, it's not. So I've on this particular version of the browser, it's actually calling command versus trying to download it. And this is giving me the directory listings of the C drive. Bad, bad, bad. Yes. So Unicode encoding, that's an example of an obfuscation attack. And it's again obfuscating the slash. Dots mean up one directory. Dot means up one directory. Up, down, down, down. So there you go. That's a directory traversal attack. All right, local file inclusion attacks, you're calling either a local file to be included in processing, or you're calling a local file to be displayed in the request. A remote file inclusion calls your file from a remote location and typically executes it locally. All right, cross-site scripting. Okay, cross-site scripting, we've got an example of that too. All right, I'm gonna go to my victims websites here. We'll go to PowerGym. We're gonna log in. Password Sam. All right, username Sam. Password test. I'm going to leave a comment. Script. Access is verified. Let's get space in there. Okay, this would normally be a comment to be displayed by anybody that visited the comments page. But instead, I'm tagging it as a script, tagging it as a script. I'm asking it for it to fire up a simple alert with the message XSS verified, and then I'm closing the script. All right, so the system, when it receives this code, instead of displaying it as text, sees it as a script to execute. And instead, it pops a pop-up. So I'm gonna hit submit. I'm gonna navigate away and back, and boom, there it is, XSS verified. All right, it's that easy to check for, but if you think about it, what's the danger in that? Well, you could leave scripts up on a website, and anybody that visits that page gets the script. Right, bad mojo, definitely. Lots of cross-site scripting vulnerabilities for decades. And how do we fix all this? You sanitize user-supplied input. So that was an example of a stored or persistent cross-site scripting. Reflected is sent back in the immediate response page. So I put what should be content to read, it's in actuality executable content, up on a website, and the next person to receive that page fires. Pretty cool. Our request forgeries, a little bit different. A request forgery is where I have an active session with a web server, for example, and I send an unauthorized or unknown transaction. Okay, so really simply, this gets way more confusing than it needs to be. All right, so here I am connected to my banking server, and I've got an actual connection, all right, legitimate, valid, session ID, the whole 9 yards. At the same time, I visit a malicious page, script executes, or hacker distributes a piece of malware to me. A script runs locally that then sends a request to transfer funds to my attacker. Maybe, I mean, e-banking Trojan might work that way. But I've got an active session established, but an unauthorized request is sent within that active authorized session. Transfer funds to the attacker, for example, or submit something different to a Facebook posting or whatever. There's different flavors of those, and it may be executed by a cross-site script. All right, so request forgeries sound identical to cross-site scripting. They're a little bit different. An unauthorized request is being sent, and those can be client-side or server-side. All right, session hijacking, taking over a session. I can replace the authorized user or server. The attacker assumes the identity of a valid entity. I'm going to show you this too. It can be initiated as an on-path attack, converts to a hijack, or it can be a sidejack attack. Web-based hijacks accomplished with cookie theft or session ID discovery prediction. Well, that sounds too much to resist. Let's take a look. All right, so my server 2019 machine, my server 2016 machine, I'm running this guy through a proxy. This is the burp suite. This is what John was talking about. Really great utility. We love the burp suite. One of the most useful in the tool chest, no doubt about it. Let me go ahead and clear my history. Start with a nice clean slate. All right, I'm not going to worry about intercept on. Okay, listeners all good, perfect. Intercept is currently off. Perfect. Let's look at the history. All right, on my server 2016 machine, I'm going to log in to PowerGem, and I know I'm not logged in because I just clicked on login. Log into SAM, password test. There's my pop-up. Nice cross-site script from the last demo. I'm now logged in. I know this because now it says log out. Okay, but I've also now got a session identifier. So my burp box, if I go to this connection and I look at the cookie information, there it is. There's my active session ID, and all I have to do is clone that. So I'm going to copy it. And I'm going to fire up Firefox, establish a connection to the same page. Notice I'm not logged in. We'll change that. I'm going to go to Developer Tools. I'm going to go to Storage. I'm going to create my own cookie from scratch. You can do that? Sure. I'm going to call that cookie ASP.NET Session ID. Get rid of the equals. Set the value to my session identifier. All right. I've just copied the session identifier and I've cloned the session token. But hold on a second, Eric, it still says log in. It didn't work. Well, I haven't refreshed the page yet. So when I refresh the page, login turns to log out, and I'm now logged into Sam's session. Sam has no idea that I'm logged into Sam's session because this really isn't an active session hijack, it's a sidejack. I've taken his credentials and I'm replaying it from a different IP, which not every website allows you to do that. This one does. So if I take a look at the club or services, for example, Sam doesn't see that. Sam goes to the trainers page. I don't see it. I go to the program page. Sam doesn't see it. You get the idea. We're two completely separate connections. Neither one sees the other one's requests because they're sent to different IPs. What we would see is a manipulation of a common shared resource, like putting something in the shopping cart or logging out. So if I was to log out and Sam refreshed, Sam is now also logged out because I ended the session. So that's a session hijack. All right, you can steal session tokens a variety of ways. Sniffing is one of the more likely to be successful. And then there's SSL TLS encapsulation, which there's ways around that too. I could actually spoof SSL certificates. Hopefully a victim requested it. We talked a little bit about how SSL TLS works. So all I have to really do is send a bogus certificate and hope that the user accepts it, even though they've gotten an error. All right, so input validation, all right, fixes most of this, right? Hey, is this expected? No way that's got scripting tags, or no way that's got SQL meta characters, or no way that's way too long. Doesn't always happen. Client-side validation, process it on the client side. Server-side validation checks on the server side, but what do we know from our previous discussion of good developer habits, right? Offload processing to the client. So client-side suppression can be bypassed. You can manipulate it after it leaves the browser. That burp suite allows me to trap and modify and resend if I like. As a matter of fact, I can send to the repeater and intruder and keep firing it off at the target. That allows for different types of wordless attacks. Burp, very powerful mojo. All right, so input validation. Okay, whitelisting allows, blacklisting blocks. We know the concept of whitelisting or blacklisting. Escaping meta characters, okay, angle brackets, single ticks, things like that shouldn't be using a username or password. Parameter pollution, thorough input sanitization, and then web application firewalls. Definitely a common countermeasure. A WAF's job is to do content inspection, looking for things like 1=1, scripting tags, angle brackets, et cetera, et cetera. So it is signature matching, looking for suspicious syntax. All right, database security. If you don't build your database queries from user-supplied input, there's no problems. Parameterized queries are prepared statements. Stored procedures should be disabled if they're not needed. Things like SP make web task, generate an HTML document with the results of a query, which we could go on for a few hours on the Sql injection. I'm just going to show you the basics and just kind of illustrate my points here. But again, if you want more of an in-depth discussion, come on back for CEH. This is the kind of thing we do all week long. All right, obfuscation, camouflage, data minimization, tokenization, hashing, salting. We've seen all these terms in previous chapters. All right, code security. You should sign your code. Excuse me, itch. Code security should sign your code. Code reuse. Remember, we have a tendency to use development kits, libraries. Code is reused for other purposes. Some developers don't vet the code they use. That is poor coding practices. Well, it works for this, let me bring it to this, and there's hidden functionality that you don't know about that leads to a potential vulnerability. All right, again, software is diverse, lots of different applications. Code repositories we talked about in the previous chapter, practicing good version control, and again, code that is no longer valid in production, dead code, should get rid of it, right? Out the door, purge it. All right, additional application security controls, integrity measurement, that goes right back to hashing, scalability and elasticity. Okay, we've seen those terms. This is the third time those have come up. We know that scaling up or scaling out is vertical or horizontal. Elasticity or expansion to accommodate higher workload is a characteristic of cloud environments. Secure coding practices. Source code elements or source code comments need to be taken out when it goes live. Web pages are famous for having developer comments, which you find some crazy stuff in web pages, like passwords for authenticated areas of the site. What? That's all fine while it's in development and it's accessible from inside the security perimeter. When that thing goes live, you're supposed to take all that stuff out. Source code comments, lots of potentially useful information. Error handling, that unclosed quotation mark before character string and password equals in SQL login ASP line 5 gave us a ton of information. All right, it should be something like, oops, you've encountered an error. 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 Nothing useful. Instead, it tells me that's a Microsoft ODBC SQL Server driver. Microsoft, so check, use Microsoft syntax. It gives me a unclosed quotation mark, character string, password equals, SQL login ASP line 5, way too much detail. which if you're in troubleshooting and development, that's really useful. Here's the problem, here's the error, let's go fix it. This goes live, you do not want that stuff pointing out exactly, pinpointing what files you're using and all that. Way too much information. All right, post data, date and timestamp, SQL login ASP, you get the idea. All right, instead if I get a generic error page, oops, you encountered an error, I might manipulate that for blind injection. That was the time delays. So revisiting that, true or false questions, 5-second delay or not, all right. All right, so error handling, suppress error messages, hard-coded credentials, bad idea. Hard-coded credentials, if they're disclosed, it's like default passwords. All right, resource exhaustion, memory leaks and memory pointers. Okay, memory management, an efficient application uses enough memory to do its job and nothing more. But every so often you'll have something that is a leaky application where it keeps staking a claim to memory and keeps staking more claims to memory. It's not really using it. And pretty soon it allocates all the system memory to the leaky application. That is poor coding practices. It needs to be rebooted or restarted. There's been a few examples of that over the years that I recall. One was in like a Firefox browser. You let it run long enough, your system's gonna lock up. All right, memory pointers. You can attack memory space. Stack pointers, extended instruction sets, base pointers. Those are all exploited in buffer overflows. And then resource exhaustion in general is, again, maxing out its capacity. All right. All right, just trying to think if there's any demos I would like to throw in addition to that. I think that pretty much covers all of our concepts we talked about in the chapter. We saw a little malware, we saw rootkit, we saw session hijack, we saw SQL injection, we saw cross-site scripting, we saw directory traversal. All right, so I think that's a pretty good reinforcement of the terms. So I hope you enjoyed the demos. But again, we've got a week long of that stuff in like CH and forensics. Look at the detective side of things. So if that is piquing your interest, we can definitely accommodate on other courses. All right, secure coding practices. That is our final chapter for our final slide for the final chapter for the final domain. We're actually now done with the official delivery part of CISSP. As we've done in previous chapters, we're going to go ahead and finish reading the summary, read the exam essentials, answer the review questions on efficientlearning.com for chapter 21, malicious code and application attacks. You're going to go ahead and grab a break in there as well because we're definitely due top of the hour. All right, we're going to resume at 5:40 Eastern to wrap it all up. All right, standing by. Give me a shout out in the chat window or a buzz on the phone if you have any questions. And see you back at 5:40 for the wrap up. How phase 1 gets completed, what phase 2 involves, what phase 3 involves, and wrap everything up, get you guys started on your weekend and started on finishing phase 1. And we'll go one-on-one for individual study schedules. All right, standing by, guys. See you back here at 5:40 for the wrap up.